Okay, so the broader question we're going to ask in this section is we want to go from point A to point B. And oh my God. Let's see what's, I can fix it. If you want to go from point A to point B, clearly there are many ways to do that. You could just connect A to B with a straight line, and that's fine as long as there are no obstacles in the way, right? Sometimes there are obstacles. So let's say that there is a obstacle here. These are obstacles. And then you need to basically plan a path which avoids the obstacles. Now, there could be an obstacle right in between. But sometimes, the straightest path from A to B is not the most optimum path, because maybe we don't want to find the shortest path, but we want to find the path which consumes least amount of energy. Or if there is, for example, if you are using Google Maps, the shortest path will have most traffic, and so you don't want to take that path, but you want to take a longer path which has less traffic, which will probably take you to your destination much faster. So all these things can be cast as an optimization problem where there is the cost, energy, time, distance, whatever you like, and there are certain constraints. Like, for example, you cannot accelerate your car faster than certain value, or you cannot go above a certain speed. If you go on certain locations, you'll hit into a bump. So all these things can be cast as constraints to the problem, and then you can use that to solve the problem. So in order to get to the point where we're doing these more interesting problems, we'll first motivate optimization. I'll teach you some of the tools we'll be using in getting to solving these hard problems in controls and robotics. So we'll motivate optimization. Okay, here's a function f of x. x2 minus x1 square. Sorry, x1 square, the whole square, the way I've written it, plus 1 minus x1 square. And a goal is to minimize f of x. And in this case, the optimization variables are x1, x2. So this is how typically a problem will be written. You'll be told minimize or maximize the function, and then the optimization variables. You can tune x1, x2 to whatever values you want, so that f of x is minimum. Okay. There are many ways to solve this problem. Ways to solve. Here's one way. You can graph this. So a graph for a function of 2 dimensions will be something like this: x1, x2. This is along the x, and draw this. x1, x2, f of x, and something in 2 dimensions or 3 dimensions in this case is going to be some curve. In fact, sorry, it's going to be a surface. And the optimum is going to sit right at the bottom. Okay, wherever f of x is minimum. So if you graph it, maybe you can just hunt down the point where the function has a minimum, and you'll get the answer. Now this trick works well for 2 dimensions, 1 dimension. There are 2 unknowns, x1, x2, or 1 unknown, but just really hard to do in 3 dimensions, 4 dimensions, when there are 4 variables and so on. Okay, another method of solving such a problem is to use just guess. Okay, you may ask, how do you go about guessing the solution for this one? Well, we see that f of x is a function which has two square terms. So this function is always positive. So we can maybe guess that one way of minimizing this is to see that the value of f of x is 0, because a square, something which has sum of squares is 0 or greater than 0. So maybe there is a solution such that f of x is 0, in which case you can see that the solution is just 1, right? If you put 1 and 1 for x1, x2, f of x is actually 0, and that is, turns out that is the optimum solution. But not all functions, not all problems that you'll get would be of this form, would be quadratic, sum of squares. A third way is to use what we learn in calculus. You need to compute df dx. That should be 0. That gives the extremum value. Extremum. So this, when you do this, you'll see that you'll get x1 equals 1 and x2 equals 1. And then the test to confirm that this is actually indeed the the values of x for which f of x is minimized, you need to do the second derivative test. If df dx square is less than 0, but it's greater than 0, it's a minimum. And then you might have seen this, if you have less than 0, it's a maximum. So at this point, you're not sure if this is the minimum or maximum, but the second derivative test will tell you if it's a minimum maximum. So that's the third way of doing this. A fourth way, and this is a way which we'll be following in the course, is to do this calculus calculations using basically a numerical package. Now, it doesn't quite do df dx. There is sometimes some algorithms will do exactly this, df dx, try to find the derivative where the derivative is 0, but some other methods might have some other fancier way of figuring out how to compute the minimum of this. So there are multiple methods, and we will not really learn about the different methods. We'll just be good users of optimization softwares. So the fourth one is do this numerically. We'll use Skippy optimize. Okay, so there are basically two types of optimization. There's unconstrained optimization, in which you'd only have a cost. A cost would be that function. Example would be the problem we just did. F of x equals 100 x2 minus x1 square plus 1 minus x1 square. Okay, so this is unconstrained because you'll see that there is only a cost. This is a cost. There is no constraint. There's nothing which says that x1, x2 follow a certain profile, or there's no limits placed on x1, x2. There could be some limits in the sense that x1 needs to be, say, less than 5, or x1 plus x2 should be greater than 4, or whatever it is not this. That's unconstrained optimization. The second class is constrained optimization, in which you will have a cost and you'll have constraints. Okay, here's another one, x1 square plus e raised to x2 is less than 2. So those are examples of constraint. The cost is some function of x1, x2. I'll just put something here. X1 square plus x1 minus x2 cube plus something like that. Okay, there's a cost and there's a constraints. So clearly, the unconstrained optimization is much easier than constrained optimization. In fact, I don't think you were maybe you taught a little bit about constraint optimization when you did calculus. To do that, what you need to do is you need to use Lagrange multipliers, and then you can solve it using the calculus trick I just told you, the df dx. Okay, but we'll not get there. We'll basically use software to do this. Okay, so let's look at a constraint optimization problem, and then I'll solve the constraint problem and the unconstrained problem using Python. Yeah, so here's a example of a constraint optimization problem. So minimize f of x, which is equal to x1 square plus x2 square plus x3 square plus x4 square plus x5 square. That's the cost. Okay, this would have you minimize over x. In this case, clearly x is x1, x2, x3, x4, x5. Okay, then the constraints are, you say, subject to x1 plus x2 plus x3 equals 5. So that's the first one. The second one is x3 square plus x4 equals 5. The third one is x1 is greater than equal to 0.3. x3 is less than 5. And then x4 square plus x5 square is less than 5. Okay, so those are the constraints. There are 5 constraints. Okay, so let's look at these constraints again. The first constraint is a linear function of x1, x2, x3. There's no squared or nonlinear terms. So squared, cosine, exponential, none of those exist. So this one is called a linear constraint, but there's more to it. It's a equality constraint. So linear equality constraints. The reason I put it there is because some optimization solvers like you to tell it about such constraints because they are usually kind of simple because they are linear. This one, however, is the second one. You can see there's an x3 square. That's nonlinear. So the moment there's one nonlinear term, this becomes a nonlinear. Since there's equality, it's equality constraint. Okay, let's go to the last equation. You can see that there's a nonlinear term, there are 2 terms, x4 square, x5 square. So that is also a nonlinear, but there's an inequality. So it's an inequality constraint. Okay, we're left with 2 more, x1 greater than 0.3, x3 is less than 5. Now you could treat them as constraints, but some optimization softwares rather would want you to put bounds. So x1, x2, x3 are variables which are bounded. They cannot have any value. So we can actually put them as bounds. So this is talking about implementation in the software. So we have bound. We say that x1, since it's greater than 0.3, x1 is between 0.3 and infinity. x3 is less than 5, which means that it's going to be between 5 and minus infinity. And then the other ones, x2, x4, and x5, write it down, x2, x4, x5. There's nothing said about those variables, so we assume that they are between minus infinity and plus infinity. Okay, now how would you solve this? Well, we could use a trick we had. We could say, for first of all, graphing is out of question. It's basically a 5-dimensional, 6-dimensional space, right? Once you include f of x, you could guess maybe 0, 0, 0 is the solution because f of x is a sum of quadratic terms. So if you put 0, 0, 0, 0, you will see that it actually violates this one. So if you put 0 plus 0, it's not equal to 5. That means 0, 0, 0 is not a solution. So you see that it's not easy to guess the solution either, right? We could use calculus, which I will avoid here, but you can do it with Lagrange multipliers. I'll just show you how to do this with Python. Okay, and it will basically do this. Now, the good thing about optimization, as in general, is that if you're doing a senior design and you can somehow formulate your design problem as an optimization problem like this, where there's a cost, there is constraints, you can actually use the same tools to solve those problems. You don't have to really only limit this to robotics. This is very general, can be used for pretty much any problem. So optimization is a very useful tool. Okay, so first of all, this is the first problem we talked about, where we knew that this is the unconstrained optimization problem, where we knew that the solution was x1 equals x2 equals 1. So I just have to give it an initial guess. I need to use minimize. So this comes from skippy.optimize. I imported that as OPT. op.minimize, give the function, which is this. You give it the method. So BFGS is a method available in unconstrained optimization. And we just run this, and it gives me 0.999, 0.99, and which is close to 1. Now, if you want more information about this function, you can go to this. Okay, BFGS. It basically gives you, that's what BFGS stands for. It's the name, the 4 authors who created the method. It basically gives you a function example, and if I want to learn this, I would just copy paste this in Python, get it to work, and then modify it for my own purposes. So what this function requires is, see if you can find the syntax. It should be right up. Not here, let's go up. Okay, that's up to. Okay, I guess we need to just look at the way it is called here, right here. Okay, method. You can see there's some called Jack. Jack is basically the Jacobian. What is the Jacobian? We've learned what a Jacobian is. It's the derivative of whatever that function with respect to the variables. In this case, f is a function of x1 and x2. So the derivative of f with respect to x1, x2 will be a 1 cross 2 matrix, and that's what they've provided. Actually, you can see it here. Derivative 0, derivative. There. This should be the derivative. This is the Rosenbrock function is a function which has a lot of bumps and ditch. It's a very hard problem to solve for the optimum, and so it basically has they provide the derivative. Just makes the life easy of the optimizer if you can provide it with the derivative, and then options display true. So that's BFGS for you. So that's the first one, unconstrained optimization. Now I decided to program the constrained optimization, the second one we talked about, the sum of squares, in 2 ways. I used a method called SLSQP. This is basically sequential quadratic programming. You don't need to know too much about it. It's just one of the many methods available in Skippy Optimize. I also used another method called trust constrained optimization. Okay, and both of them it's pretty much like this. Sometimes one of them is faster than the other. Sometimes one will give you a solution, one won't. And so you just need to know the tools you have. So let's run this. This is the solution produced by the SLSQP. I'm going to copy this. Save it here so we can confirm that it's the same solution we get with the other method. Okay, so the 5 variables are this. You can see it's clearly not 0, 0, 0. It's something else. But this satisfies all the constraints. So what goes on here is the cost. I need to give the bounds. Remember, I talked about the bounds. Only one of them had it's 5. I think there's a inf1. This should give you the upper and lower bounds. Negative, negative, negative. So that's 5. Let me just go here. So the first line is upper bound. Second line is lower bound. I thought this was 3. I might have made a mistake here. Let's just change that. Okay. And we can run. I'm sure it'll produce produces a new, different solution. Interesting. Let's copy that. Okay, and then we have all the inequality constraints should sit in one place. So that's all inequality constraints. All the equality constraints sit in one place. And so that's put up here. And then you have to give an initial guess. Okay. Okay, so that's SLSQP. If you do this with this one, I'll have to change this back to 3. It was not 0.3. Let's run this. Okay, it gives some messages, warnings. Some of them are bad, some of them are good. But let's look at this solution, which it produced. And right here. Okay, so first x1 is the same, x2 is the same, x3, x4, and the last one is actually practically 0. It's -8. Okay, so it produces the same solution as both methods produce the same solution, give the same initial guess. Now, sometimes it does happen that you give an initial guess and it won't converge. So it also depends on the initial guess. So you want to just try a bunch of initial guesses before you're sure. Sometimes if you give initial guess, it'll give you one solution, but if you change the initial guess, it'll give another solution. That's because of all these methods usually give you a solution close to whatever initial guess you gave it. So it's always a good idea to try these optimizations with multiple initial guesses, just randomly strewn. And some of them will give you a solution, some won't. Sometimes you'll give a different solution, and just choose the one which gives you the minimum cost, right? Okay, any questions? So if you want to read more about this, I have it here in the documentation. It's the same link. It goes to SLSQP. So what it needs is the cost, the constraints, equality constraint, inequality constraint, and the bounds. So those 3 things. And then they have an example here, which I pretty much took it and then I modified for my own purpose. If you want to know more about the other one, you can press this control and click that trust constraint. Now this one you can see is slightly different. It wants you to give you f of x, and it doesn't really distinguish between inequality and equality constraint. Just wants you to put everything in one place as c of x, and then the bounds. Okay. So that's pretty much how it is. So take the problem and then modify it for take the code and then run it on your end, see if you get the same solution, and then modify it for own purposes. Any questions on this?